Hello and welcome to the MAML Manual. I'm Sebastien.
And I'm Iris.
And today we'll be covering 9 problems from Meet 4, Topic 2, Logs and Log Equations. Without further ado, let's jump right into it. Since this topic is called Logs and Log Equations, it'll be helpful to know what a log actually is before we jump into some of these problems. So taking a look up here, if we have the equation b to the x is equal to a, then this statement is true. Log base b of a is equal to x. Up here we have our normal exponential function where we have some base, we raise it to a certain exponent, and we get our answer. When we have a log, we keep the same base, but we swap the exponent and the answer. So instead of the exponent being our input, our answer is now our input. Okay, so we are swapping the inputs and the outputs. Now, when we get to Meet 4, Topic 4, which is functions, that has a special name. When we swap the inputs and the outputs, they become inverse functions. So you can think of a logarithm as the inverse of an exponential function. We'll dive into more details about inverse functions in the 4th topic for this meet. But for now, all you need to know is that exponential functions and logarithms are inverses because we swap the input and the output. So just as an example, before we move on to some problems, we know that 2 cubed is equal to 8. So this is a true statement. So down here, we would say the log base 2 of 8 is equal to 3. Again, we are swapping the exponent and the answer. Here we plug in the answer and we get out the exponent. Now, in most cases, we actually do write the base here. For example, this logarithm has a base of 2, but there are 2 exceptions to that rule. If there's no base written, if the problem just says, take the log of 100, without there being a base there, then we call this a common log, and a common log always has a base of 10. So we could rewrite this as being log base 10 of 100, and we know that we have to square 10 to get 100, so the answer would be 2. Now the other special log is called the natural log, and we write that ln, the natural log. And the natural log has a base of e, where e is the number 2.7182818, so on and so on. If you see ln, this is the natural log, and it can be rewritten as log base e. So the common log and the natural log are just 2 special cases of logs. They still function in the same way. It's just that instead of writing the base out, we have special ways of denoting those logs. Now, there are tons of properties of logs that I'm not going to take the time to individually cover before we get into the problems. When we encounter those properties or those rules, I will make sure to bring them up. However, if you want a comprehensive list of all of the log properties or log rules that you should know for the Meet, you can check them out in the description. I have a link to a Google Doc where I've listed all of the properties that you should know for the Meet. Alright, so check out that link below. I'm not going to cover them now, however, I will bring them up when it's called for in the problems. Alright, enough introduction, let's jump into our first problem of the video. If log of a is equal to 0.21 and log of b is equal to 0.09, find log a squared times b. So you'll find that when we're dealing with logarithms, we don't normally put parentheses around our input. However, when we actually solve the problems, I like to put those parentheses there just so that it's crystal clear what we are inputting into the log. Okay, so really I would appreciate it if it looked like this, where our parentheses are around our input. So log b would be log of b, and this one would be log of a squared b. So normally you won't find those parentheses there, but if we want to be absolutely clear about what we are inputting into the logs, that's what we're going to do. Okay, so I'll often write it this way for the video. So now we have to use some properties of logs in order to rewrite the expression over here. So we currently have log of a squared times b. We can use the product rule of logs to split this up into a sum. So I would say that this is equivalent to log of a squared plus the log of b. And then from that point, we can use the power rule of logs to pull this 2 to the outside. So this is going to be equivalent to 2 multiplied by the log of a plus the log of b. Again, if you don't know the rules that I just applied to this problem, check out that Google Doc in the description of this video in order to find that full list. Okay, now from that point, we know what the value of log of a is, and we know what the value of the log of b is. So we can just replace log of a with 0.21 and replace log of b with 0.09. So we would say that the answer is 2 times 0.21 plus 0.09. 2 times 0.21 is 0.42, and then we're adding 0.09. So our final answer to this problem is 0.51. All right, let's move on to the next problem of this video. Find the value of the k if log base 2 of 8 is equal to k times log base 8 of 2. So log base 2 of 8 is actually the exact same problem that I showed you before we jumped into the problems for this video. So remember, logs tell us the base, and we are inputting the answer, and the output is the exponent. So the question is, 2 raised to what power gets us 8? And that answer is 3. So we know that the left side of this equation evaluates to 3. Now, let's evaluate log base 8 of 2. The question is, 8 raised to what power gets us 2? Well, we know that the cubed root of 8 is equal to 2, and we can rewrite the cubed root in exponential form. So we would say that 8 raised to the 1/3 power is equal to 2. Therefore, the answer to this is 1/3. So we can say that 3 is equal to 1/3 times k. Now that we have that, it'll be very easy to solve for k, but before we do that, I want to point something out that's important. These logs, notice, we have a 2 and an 8 and a 2 and an 8. The only thing different about these is that we've swapped the base with the input, okay? So here we have 2 as a base, 8 as an input. Here we have 8 as a base and 2 as an input. Now notice that their answers are reciprocals of one another. So this is called the reciprocal rule. If we have log base b of a, it is equal to 1 over the log base a of b. In other words, log base b of a and log base a of b are reciprocals. So while it wasn't necessary to know this fact to solve this problem, it is something to keep in mind because more advanced problems might use this fact. So just remember, when we swap the base and the input, the logs become reciprocals of one another. Alright, now to actually answer this question, we have said that 3 is equal to 1/3 k. Therefore, if we multiply 3 on both sides, we would say that 9 is equal to k. So our final answer to this problem is 9. The takeaway from that problem, remember the reciprocal rule. Alright, let's move on to our final 3-pointer of this video. Alright, this problem is asking us to simplify the following. Log base 27 of 9 times the 4th root of 27. Remember at the beginning of this video that I said logs and exponential functions are inverses of one another. That means that the following fact is true. If we have log base b, and then inside of that we have b raised to the x power, that is just going to be equal to x. That means that in this problem, we want to rewrite the input of this log as a power of 27. And once we do that, it will be very easy, because we'll say the log base 27 of 27 raised to whatever power will be equal to that power. So let's rewrite this input as a power of 27. Let's start with 9. 9 is equal to 27 raised to a certain power, let's call it a. Well, we know that the cubed root of 27 is equal to 3. And then if we square both sides, that would equal 3 squared, or 9. So the cubed root of 27 squared is equal to 9, and we could rewrite that as 27 raised to the 2/3 is equal to 9. So we can come up here and replace our a with 2/3. Now for the fourth root of 27, that's easier. The fourth root of 27, we can just rewrite that as 27 raised to the 1/4 power. So our input is now 27 to the 2/3 power times 27 to the 1/4 power. And if we remember our exponent rules, that can be rewritten as 27 raised to the 2/3 plus 1/4. And now if we get a common denominator, that's 27 raised to the 8/12 plus 3/12. And therefore it is 27 raised to the 11/12. So now this is what we are simplifying. Log base 27 of 27 raised to the 11/12. And as I mentioned over here, if this base and this base are the same, then the answer is just going to be the exponent. So the 27 and the 27 cancel, leaving us with the answer, which is 11/12. And that's our final answer. Now the takeaway from this problem is to remember that logarithms and exponential functions are inverse functions. So when we do the log base b of b to the x, we will get out our original exponent. Alright, let's move into the 4 pointers of this video. Find the value of log base 7 of 8 times the log base 6 of 7 times the log base 5 of 6 times the log base 4 of 5. Now looking at this problem, it initially seems pretty crazy. How are we expected to evaluate the log base 7 of 8? That's not going to come out to a nice number. However, these types of problems actually have a very nice shortcut. So I am going to show you the longer way to solve it, but then once I show you the longer way, you'll be able to recognize a shortcut that will allow you to solve this problem in about 15 seconds. Now the key to the long way to solving this problem is the change of base formula. Okay, so this is another one of those formulas that is listed in the Google Doc in the description of this video. So if you need a reminder, we can rewrite the log base b of a into any base we want to. It'll be the log base c of a over the log base c of b. So let's go ahead and do that in this problem, and let's pick any base we want to. Now to solve this problem, it won't actually matter what base we pick, so let's just choose the natural log. Why not? Let's go log base e. So rewriting this, I'm going to say the log base 7 of 8 is going to be equal to the natural log of 8 over the natural log of 7. And I'm going to do that for each one of the terms. So the next one is going to be the natural log of 7 over the natural log of 6. And then we're going to multiply it by the natural log of 6 over the natural log of 5. And then finally, we're going to multiply this by the natural log of 5 over the natural log of 4. Now, conveniently, we are able to cross out many of these terms. We can cross out ln7, ln7, ln6, ln6, and ln5, ln5, leaving us with the expression the natural log of 8 over the natural log of 4. But now looking at this, it's still not nice numbers, right? We can't evaluate the natural log of 8. That's not going to come out to a nice number. Well, you'd be right. Natural log of 8 doesn't come out to a nice number. However, this ratio does come out to a nice number, and we can actually use the change of base formula to convert it back into a form that looks like this, right? Because we have the natural log over a natural log. So currently we're looking at an expression that looks like this. So let's get it back into this form. So the natural log of 8 is going to be a. So it's going to be the log base something of 8. And that base is going to be this input down here. So the base b is going to be 4. So we can rewrite the natural log of 8 over the natural log of 4 as the log base 4 of 8. Now this is something that we can evaluate. We need to rewrite 8 in terms of a power of 4. Well, we know that the square root of 4 is equal to 2. And then if we cube both sides, it would equal 8. So the square root of 4 cubed is equal to 8, or in other words, 4 raised to the 3 halves is equal to 8. So we can rewrite this as the log base 4 of 4 raised to the 3 halves. And remember from the last problem that when we have the log base 4 and then we have 4 raised to something, these 4's will cancel out, leaving us with our answer 3 over 2. So the answer to this problem is 3 over 2, and that is our final answer. Now remember, I had said there was a shortcut to solve this problem, and there is. If we take a look up here, we notice that there are a lot of bases and inputs. We can cancel out some of those bases and inputs. So notice, we have the log base 5 of 6, and then we have the log base 4 of 5. Well, I notice we have a base of 5 and an input of 5. So those are going to go away. Over here we have a base of 7 and an input of 7, so those go away. And then we have a base of 6 and an input of 6, so those go away, they cancel out, leaving us with an input of 8 and a base of 4. Those are the only things that don't cancel. So automatically, just looking at this problem, we can already get to this step here, where we have a base of 4 and an input of 8. So you can take the time to write it out with the change of base, and this kind of shows why it works. Or you can just take a look at this problem up here and say, okay, I know I have a base of 7 and an input of 7, so those are going to cancel out. I would say that once you know how this works, I would recommend just using the crossout method without taking the time to write all of this out. With that problem out of the way, let's move on to the next 4-pointer of this video. Alright, now we are getting into the reason why this topic is called logs and log equations. This is definitely a log equation where we're solving for x. The 4 and 5 pointers will definitely involve some form of solving for a variable, which normally is x. So solve for x if the log base 3 of 5x squared minus 8x minus 4 minus the log base 3 of x squared minus 6x plus 8 is equal to 3. Now in order to solve this problem, we need to know the quotient rule of logarithms. Again, all of these rules are listed in the Google Doc in the description. So if we have the log base b of m, and we subtract the log base b of n, that will equal the log base b of m over n. Now, super important, in order for this to work, the bases have to be the same. So luckily in this problem, we have base 3 and base 3, so those are the same, but if those weren't the same, we would have to take that into consideration as well. So using this knowledge, let's rewrite the left side of this equation. We can say that that entire thing is going to equal the log base 3 of our first input divided by our second input. So it's going to be 5x squared minus 8x minus 4 over x squared minus 6x plus 8. And that'll be equal to 3. Now, in order to get rid of this log, let's have both of these sides be the exponents, and let's have the base be 3. Remember that exponential functions and logs are inverses of one another. So the 3 raised to the log base 3 is going to cancel, leaving us with the input. And then we're going to have 3 raised to the third power over here. With this canceling, we're left with 5x squared minus 8x minus 4 over x squared minus 6x plus 8 equal to 27. Now let's multiply this to this side, so we can say that 5x squared minus 8x minus 4 is equal to 27 times x squared minus 6x plus 8. If we distribute, we get that 5x squared minus 8x minus 4 is equal to 27x squared minus 162x plus 216. Now, if we get everything on one side in order to solve for the quadratic, we would say that 0 is equal to 22x squared minus 154x plus 220. Thankfully, there is a common factor of 22 here, so we can divide each of these terms by 22 to get that 0 is equal to x squared minus 7x plus 10. From that point, that's a pretty simple quadratic to factor. We have our factor x over here. We would say that we need two numbers that multiply to 10 and add to negative 7, and that would be negative 2 and negative 5. So factoring this would be x minus 2 times x minus 5. So we would say that x could be 2 or 5. However, that is not our final answer because we need to make sure that both of these values of x are valid to plug in to logs. One condition of logarithms is that we cannot input 0 or a negative number. So the input into a logarithm must be greater than 0. If we have values of x that make the inputs 0 or less, then they are invalid. So we have to test that out. So let's start with 2. Plugging in 2, we have 5 times 2 squared, which is 20, minus 8 times 2, which is 16, minus 4. So we have 20 minus 16 minus 4, which is 0. So we have the log base 3 of 0, which is invalid. That's undefined. So 2 is not going to be a valid answer. Now if we test 5, hopefully it does work. 5 times 5 squared is 125, minus 8 times 5 is 40. So we have 125 minus 40 minus 4, which is 81. So that is a valid input. So over here we have 5 squared minus 6 times 5 plus 8. So we have 25 minus 30 plus 8, which equals positive 3. So again, that's another valid input. So log base 3 of 81 minus the log base 3 of 3 equals 3. That is a true statement and we have valid inputs. So 5 is our only valid value of x. So our answer to this problem is 5. I would say there are two key takeaways from that problem. So first, this is the quotient rule of logs. It's a very important one to know. Again, I have a full list of all of the properties of logs that you need to know in the description in a Google Doc. The second takeaway is that when you get answers to a quadratic or a cubic, when you're solving this type of problem, you need to plug them back in to the original equation in order to confirm that you have valid inputs. And that concept is something that you should be familiar doing from exponents and radicals, which was Meet 3, where you plug in the answers you get back into the equation to ensure that they work. But this is just another reminder that you also need to do that for log equations. Okay, with that problem out of the way, let's move on to our final 4-pointer of this video. All right, let's evaluate 5 raised to the log base 5 of 36, raised to the log base 6 of 7, raised to the log base 49 of 19. So the key to solving this problem is remembering that exponential functions and logarithmic functions are inverses of one another. So if we have any base, and then we raise it to the log base b of an input x, the answer to that is just going to be this input x. The base raised to the log base b cancel out. So here, when we have 5 raised to the log base 5 of 36, that cancels out, leaving us with 36. So now let's continue that pattern. We now have 36 raised to the log base 6 of 7. Now we can't just cancel out 36 and 6. We are going to need to do a little bit of rearranging. We can rewrite this as 6 squared raised to the log base 6 of 7. And based on our rules of exponents, we know that if we have 6 squared and then raised to another exponent, we can just multiply these exponents. So that becomes 6 raised to the 2 times log base 6 of 7. And then using our power rule of logarithms, we can move this 2 to the inside. So we'll say that it now becomes log base 6 of 7 squared. And we know that 7 squared is 49. So we now have 6 raised to the log base 6 of 49. The 6 and the log base 6 cancel, leaving us with 49. So now finally we're left with 49 raised to the log base 49 of 19. And conveniently that 49 and the log base 49 already cancel out. So those cancel, leaving us with the answer 19. This wasn't too hard of a problem. Again, the key is just to remember that exponential functions and logarithmic functions are inverses of one another. Alright, let's move into our first 5-pointer of the video. Alright, solve for x if 8 times the log base 4 of x squared plus 5 is equal to 7 times the log base 4 of x squared. Now this is where I really wished MAML used parentheses to say what the input of the log was. If they were doing that, they would have put parentheses around this x and parentheses around this x squared. That just makes it crystal clear what is being inputted into the log. Now that we have this expression, we are going to solve this as if it were a quadratic. And now in order for you to visualize that clearly, I'm going to say that the log base 4 of x equals a. So a is just a placeholder, but it will allow us to better visualize how to solve this problem. So if the log base 4 of x is a, then we get the expression 8a squared plus 5 is equal to 14 times a. Now this just looks like a standard quadratic that we know how to solve. If we subtract the 14a, we get that 8a squared minus 14a plus 5 equals 0. From that point, we would want our factor x. We want two numbers that multiply to 40 but add to negative 14. And that would be negative 10 and negative 4. So we get 8a squared minus 4a minus 10a plus 5 equals 0. The common factor is 4a, and then we have 2a minus 1. And then the common factor here is going to be minus 5, and then we have 2a minus 1 equals 0. So in factored form, that would be 4a minus 5 times 2a minus 1 equals 0. And therefore, here we would say a is equal to 5 over 4. And over here we would say a is equal to 1 over 2. Now that we've solved for the value of a, we can solve for the values of x. So instead of saying a is equal to 5 over 4, we can say that the log base 4 of x is equal to 5 over 4. So given that we have the log base 4 of x equals 5 over 4, and also we can say that the log base 4 of x equals 1/2. Now we have to solve the following equations for x, and that gets us back to what the definition of a log is. Given that the log base 4 of x equals 5 over 4, then we can rewrite this to say that 4 raised to the 5 over 4 is equal to x. Similarly, over here, we can write 4 raised to the 1/2 is equal to x. Now this one's pretty easy. 4 raised to the 1/2 is just the square root of 4, which is 2. So over here, we can say that x equals 2. But 4 to the 5 over 4 is a little bit trickier. How do we put that into simplest radical form, which is what is required for this question? We can break this up into 4 raised to the first power times 4 raised to the 1/4 power, and then we can rewrite 4 to the 1/4 power in radical form. We can say that it is the 4th root of 4, but that's actually not in simplest radical form because 4 itself is a square number. So we can rewrite this as 4 raised to the 2 squared, and that's the same thing as saying the square root of 2. So 4 to the 5 over 4 is equivalent to 4 times the square root of 2. So we found that the two values of x are 2 or 4 times the square root of 2. Now looking up here, those will both be valid inputs because we are just inputting x, and here we are inputting x squared. And so that means we are inputting positive values into a logarithm, which is valid. That is a valid thing to do. The only problem is if we input 0 or a negative number into a log. So the final answer to this problem would be that x is equal to 2 or 4 times the square root of 2. I would say that this is a somewhat common 5-pointer where they have you solve a quadratic, and we kind of do a replacement here where the log base 4 of x we can replace with another variable and then solve that quadratic. So it's definitely a good skill to have. Alright, let's move on to the next 5-pointer of this video. Alright, so in this one we need to solve for x, so this is your standard log equation. However, we have to note that the bases are not the same. Okay, we have log base 8 and then we have log base 4. So we're not going to be able to immediately apply the quotient rule like I would want to in this problem. However, we notice that these are conveniently both powers of 2. This brings me to a new logarithm rule that you should know, and it is what I like to call the power base rule. So if we have log base b raised to the c power of a, we can pull this exponent out to the outside, and it's going to be the reciprocal of that exponent. So log base b to the c of a is equal to 1 over c times log base b of a. Again, I'm not sure this has an official name, but I like to call it the power base rule. And we are able to apply it to this problem. Because we can say the log base 8 of 9x plus 5 is equal to the log base 2 to the third power of 9x plus 5, which is equal to 1/3 log base 2 of 9x plus 5. So if this is equal to 1/3 times the log base 2 of 9x plus 5, and we're multiplying it by 3, the 3 and the 1/3 will cancel out, leaving us just with log base 2 of 9x plus 5. We can see a similar thing happen with the next term. We'll say that the log base 4 of x squared minus 1 is equal to log base 2 squared of x squared minus 1, which is equal to 1/2 log base 2 of x squared minus 1. Now we have a 1/2 here. We're multiplying it by 2. 2 times 1/2 cancels out, leaving us just with log base 2 of x squared minus 1. So we can rewrite this with a common base of 2, and we can say that log base 2 of 9x plus 5 minus log base 2 of x squared minus 1 is equal to 2. And now, given that the bases are the same, we can apply the quotient rule. So we would say that log base 2 of 9x plus 5 over x squared minus 1 is equal to 2. Now we've got to cancel out this log, so we treat these as exponents and we have a base of 2. So the 2 and the log base 2 cancel, so we'll say that 9x plus 5 over x squared minus 1 is equal to 2 squared, which is 4. Multiply the x squared minus 1 on both sides. We get that, let's work up here, 9x plus 5 is equal to 4x squared minus 4. And then because this is a quadratic, we're going to want to get everything on one side. So we will say that 4x squared minus 9x minus 9 equals 0. If we have our factor x, we want two numbers that multiply to negative 36 and add to negative 9. And that would be negative 12 and positive 3. So we end up having 4x squared minus 12x plus 3x minus 9 equals 0. The common factor is 4x. And then we have x minus 3. And then the common factor is plus 3. And we have x minus 3 equals 0. So in factored form, this is 4x plus 3 times x minus 3 equals 0. Therefore, x is equal to negative 3 over 4 or 3. But remember, that's not our final answer because we need to plug those values back in to this equation. When we multiply negative 3 over 4 by 9, we get negative 27 over 4. 5 can be rewritten as 20 over 4. So we have negative 27 over 4 plus 20 over 4, and that equals negative 7/4. We cannot plug in a negative value into a log, therefore negative 3/4 is not a valid answer. If we were to plug in 3, we would get 9 times 3 plus 5, which is 27 plus 5, which is 32, which is a valid input. And then over here, we have x squared minus 1, so it's 3 squared minus 1, so it's 9 minus 1, so it's 8. And again, that's positive, so that's going to be a valid input. So 3 does work, negative 3 over 4 does not work, so our answer is 3. So the key takeaway there is a new rule. We have the power-based rule, and then of course, we do all of this work. Once we get our 2 answers from a quadratic, or we could get 3 answers from a cubic, we need to test those answers into the original equation to ensure that they work. With this problem out of the way, let's move on to our final problem of the video. Alright, here's a bit of a mess of a problem. Solve for x if that entire thing equals log base 10 of 1 over x. Now immediately when I see this, I think change of base. However, we do have these terms in the denominator that are making this problem a little bit tougher. So I want to get these terms from the denominator into the numerator. To do that, I'm going to remember the reciprocal rule. The reciprocal rule states that if we have the log base b of a, that will be equal to 1 over the log base a of b. So when we have this log base 4 of 3 in the denominator, so we have 1 over log base 4 of 3, that will be equivalent to swapping the base and the input. So it will be equal to log base 3 of 4. So in order to move this log into the numerator, all I have to do is swap the base and the input. And I'm going to do that for all of the terms in the denominator. So I end up getting log base 2 of 3 times the log base 3 of 4 times the log base 4 of 5 times the log base 5 of 6. Notice that I swapped the 5 and the 6. Times the log base 6 of 7 times the log base 7 of 8. Again, I swapped the base and the input. From that point, that looks like a problem where we can use the change of base formula. And remember the shortcut that I told you. I noticed that we have an input of 3 and a base of 3. An input of 4 and a base of 4. So what I can do is I can cancel all of those that are the same. So I cancel the 3 and the 3, the 4 and the 4, 5 and 5, 6 and 6, 7 and 7, leaving us with a base of 2 and an input of 8. So this entire stretch of logs ends up evaluating to log base 2 of 8. And that's easy. That's just 2 raised to what power gets us 8? And the answer is 3. So we end up getting this entire left side of the equation is equal to 3. So we can say that 3 is equal to log base 10 of 1 over x. Now notice in this problem, they actually say log base 10. If they could have just left out that base and we still would assume that the base is 10. So weird, normally MAML and other sources don't write out that base because it's the common log. So just a reminder, if it weren't there, then we would assume that the base is 10. Okay, so now that we have this expression to get rid of the log, we want to treat these as exponents and have the base as 10. So we're going to have 10 cubed is equal to 10 raised to the log base 10 of 1 over x. 10 cubed is equal to 1,000. So 1,000 is equal to 1 over x. So therefore, if we swap the x and the 1,000, we will get our answer. We will say that x is equal to 1 over 1,000. And that is our final answer. So this problem combined a few of the rules that we already know. It combined the reciprocal rule, which was super useful for getting these terms out of the denominator into the numerator. And then it also used our knowledge of the change of base rule. We didn't actually do that out fully. We just remembered the shortcut that we learned in a previous problem. And then from that point, we just had some basic log mechanics. We know that exponential functions and logarithmic functions are inverses of one another, which allowed us to do the following. All right, with that problem out of the way, that concludes this video on logs and log equations. This was our video on 9 problems from Meet 4, Topic 2, Logs and Log Equations.
Thank you for watching.
I'm Sebastian.
And I'm Iris.
And we're the MAML Manual.